So here we have a very simple script. All it does is picks a particular size for our Hilbert matrix, so n is the dimension along either direction, and then it sets up the Hilbert matrix. So bsxfun allows us to iterate a vector with its transpose, and notice that we're one less on one of the vectors to emulate what we need for the Hilbert matrix. So this gives us an array of values for the exponents, and then we take the element-wise inverse of this to give ourselves the actual Hilbert matrix. We'll then attempt to try to invert it to see what that looks like, and then we'll also look at the condition number. So if we run this script, we see we have a particular output. So here's our argument, here's the value of our exponents, and here's our Hilbert matrix. So we can see the inverse of the Hilbert matrix has some problems. This is times to the 1,000, and any one of these particular terms should be roughly equal in magnitude. But we can see here the smallest term is several hundred times smaller than the largest term, which means that any particular one of these coefficients can have difficulty competing with the far stronger other coefficients. And we can see our condition number here is very, very large. So what this means is when we have our mass matrix, because remember this is essentially what our mass matrix would become for the monomial basis, when we have our mass matrix that we're trying to solve for the time derivative of our coefficients, we're going to have to invert our mass matrix. And so if even at fifth order or fourth order we're having trouble inverting this mass matrix, you can imagine it doesn't bode well for extension to arbitrary high order.